Before we get into our next new math topic, we're going to do a short review of the exponent laws from your algebra days. So the first thing we're going to do is review two exponent formulas that you learned in your old algebra classes. And then we're going to use one of those formulas to help us see how we can share a secret number. And in fact, this is going to give us a look ahead to some of the cryptography stuff that we're going to be doing later. So first of all, if you have two numbers multiplied together, 5 to the 4th times 5 to the 6th, what's another way of writing that? And I'm not talking necessarily about a simplified form, just what's a different way you can write that. Well, if we write what those numbers actually mean, 5 to the 4th means 5 times 5 times 5 times 5, and 5 to the 6th, very similarly, except now you have 6 factors of 5. So when you multiply those two together, you're going to get the first 4 5s, and then the next 6 5s. And if you want to know how many factors of 5s there are altogether, well, we just count them up, and we get 10. So we get 5 to the 4th times 5 to the 6th equals 5 to the 10th. And in fact, we can do this more generally. If we're trying to multiply a to the b times a to the c, we can think of a to the b that has b factors of a to the c has c factors of a. So altogether, when you multiply those together, that tells you that a to the b times a to the c has b plus c factors of a. And so you get a to the b times a to the c equals a to the b plus c. All right, so similarly, if you do something like, say, 5 to the 4 to the 6, now this is taking an exponent to an exponent. Well, what does that mean? Well, again, to the 6th power means you multiply 5 to the 4th by itself 6 times. And what I want to again do is count the number of factors of 5 that we have. Well, we have 6 copies of 5 to the 4th. And each copy of 5 to the 4th has 4 factors of 5. So that's really a multiplication problem, right? So if you want the total number of factors of 5, we take 6 times 4. That gives you 24. And therefore, 5 to the 4 to the 6th power gives us 5 to the 24th. And again, we can think of this more generally. If we have a to the b all to the c power, you can think of that as a to the b multiplied by itself c times. So if you're going to count the factors of a, you get c factors of a to the b. And for each of those factors of a to the b that has b factors of a, that again is a multiplication problem. If you count all the factors of a, you get b times c copies of a, which means that a to the b to the c is equal to a to the b times c. Right? So when you take an exponent to an exponent, that just means you multiply those exponents together. All right, so to summarize those two, if you have a, b, and c that are integers, what you have is that a to the b times a to the c is equal to a to the b plus c. And if you take a to the b to the c power, then you get a to the b times c. Now, I want to note that a lot of times we use these exponents are going to be doing computations mod n, where n is some integer, and these laws also work in those cases as well. And also, these laws are going to help us use exponents to do some really effective cryptography, and I'm going to give you a little taste of that here. So suppose that you and your friend Jojo are in the following situation. It's very uncomfortable, right? So first of all, you want to share a number with each other that is secret to just you two, but is secret from everyone else. However, you are in a very precarious situation because all of your communication is being monitored. So you can't just go tell each other what that number is. Somebody will hear, and then your secret will be out. So the question is, how can you agree on a number without anybody else knowing what that number is? Well, turns out we can use exponents for that. So here's the process that we're going to go through. So first of all, you're going to agree with each other on two integers n and g. Now, when you agree on this, of course, everyone's going to know this because anytime you communicate any integers directly, everybody knows about it because all of your communication is being monitored. So those aren't going to be the numbers that you're going to share. You're just going to use them to get it. So now what you're going to do is you're going to make up some number, an integer, a0, in your head. Now, you're not going to tell anybody about that, even Jojo. Because remember, anything you tell Jojo, somebody else is going to hear, and then everybody will know. Jojo's going to do the same thing. They're going to make up a number, b0, in their head, and again, they're not going to tell anybody. They're going to keep a secret from everyone. then what you're going to do is you're going to tell JoJo what g to the a0 power is. You're going to take your secret number and take the g, that number that you agreed upon and everybody knows, you're going to take g to that power mod n. And again, everybody's going to know this because you're telling this to JoJo. JoJo is going to tell you what g to the b0 mod n is. And again, everyone's going to know that. However, the thing is, computationally, depending on, as long as these numbers are big enough and complicated enough, figuring out what A0 and B0 is from those numbers is going to be not exactly impossible, but impossible for the at least for a while, right? I mean, computation-wise, they're never going to find out what those numbers are. So then what you're going to do is you're going to take JoJo's number to the A0 power. And again, nobody knows what that A0 power is except for you, but you're going to take the number JoJo gave you to that A0 power mod n, and it turns out this is going to be your shared number. JoJo is going to do the same thing, except JoJo is going to take your number and take it to the B0 power mod n. And I claim that this is the same shared number that you found from JoJo's number. And the thing is, we can derive this, we can verify this using exponents. So if you want to look at your numbers, your number and JoJo's number, well, JoJo gave you g to the b0 mod n, and you computed g to the b0 and took that one to the a0 power. But using that second law of exponents, you get g to the b0 times a0, right? Now, JoJo is going to do something very similar. You gave JoJo g to the a0 mod n. JoJo is going to compute g to the a0 to the b0 mod n, and then when you use that second exponent law, you get g to the a0 b0. Now, since a0 times b0 is the same as b0 times a0, it turns out that your numbers, g to the b0 a0 and g to the a0 b0, are exactly the same number. They are equal. So even though neither of you chose that particular number by yourselves, by combining the numbers that you made up in your minds, you were able to agree upon a number that is now secret to you and a secret from everyone else. And just to give you a heads up, this is something that's called the Diffie-Hellman-Merkle protocol. We're going to use this, we're going to study this in more detail later on to find out how we can share keys with one another over a public channel. All right. So, yeah, and we will see that later. So, just so you know, I didn't make any activities for this particular video. This is just to get you ready for the next video, which is on Euler's theorem. So you can go ahead and look at that one and work on the activities associated with that video.